All right, different vessel and a different time. So since I last checked in with you all in Alaska, I have temporarily relocated to Japan, and I'm currently sitting on the helicopter deck of the Japanese drilling vessel Chikyu. And Chikyu is currently parked above the Japan Trench. So this is where seafloor goes to die, all right? So about 7 kilometers below where I'm currently located is a spot where the Pacific plate is being subducted down and underneath the plate that holds mainland Japan on it. And we're currently located above a spot that's right at the tip of that overriding plate, the so-called accretionary prism or accretionary wedge. And this ship is drilling down through that overriding plate and is aiming next week to cross through the subduction zone fault, the megathrust fault, down into the subducted plate. And we'll know that we're in that subducted plate when we get to really deep sea sediments and basalt. All right, so ultimately the lithosphere of the subducted Pacific plate is made out of basalt. That basalt will have pillows at the top, a sheeted dike complex below that. Eventually it'll get down into gabbros and then into the mantle section of the plate, peridotite. In Alaska, we looked earlier at how oceanic crust is made, and underneath me here is how oceanic crust ends, where its journey ends and its story ends. It gets recycled into the mantle at that point. Water coming out of the sediments at the bottom of the ocean, sediments riding on top of that subducted plate, that gets released into the surrounding mantle. And one of the tricky things about water is when it's present in that mantle peridotite, it helps it to melt. And so that production of magma that occurs in the wedge of mantle that's immediately above a subducted plate ends up producing the molten rock that feeds the overlying volcanic arc. So Mount Fuji in Japan is a classic example of a composite volcano or a stratovolcano. Where it's getting its magma is from this partial melting of the mantle due to the subduction that's happening 7 kilometers underneath where I'm sitting right now. This is the spot where on March 11th, 2011, a giant earthquake took place. All right, this was a magnitude 9 event. Some scientists would say a magnitude 9.1. It's called the Great Tohoku earthquake. And it not only was the largest earthquake ever recorded in Japan and the 4th largest earthquake ever recorded by modern seismographic equipment, but it also generated an enormous tsunami. And that enormous tsunami was maybe 10 centimeters high right here at this spot, but then spread out at about the same rate that a jet airplane travels, and an hour later washed up on the shore of Japan over to the west here, and unfortunately caused a great amount of destruction and took a great many lives. So the expedition that's happening right here, right now, is largely motivated by the question of how do we save lives? How do we make coastal communities that are constructed next to subduction zones safer for the people who live there? In order to do that, we need to understand how oceanic lithosphere ends, all right? What are the dynamics of this convergent plate boundary that subducts old oceanic lithosphere back into the mantle? Scientists came here about 1 year after that great earthquake, and they drilled down to the plate boundary, and they found that it was still hot from the frictional sliding from that great event. We're here now another 12 years later, so 13 years after the quake, in order to figure out how the plate boundary has changed during that time. Has it begun to heal through mineralization? Has it continued to shift? So these sort of decadal scale observations are really key for figuring out how plate boundaries evolve through time. I'm sitting at the western edge of the Pacific plate. This vast sheet of oceanic lithosphere covers a huge proportion of the surface of the planet Earth. You're very unlikely to see it because it's at the bottom of the largest body of water on Earth. But we know it's down there. We have sampled it directly through missions like JTRAC and JFAST, and we have sampled it at other ocean drilling expeditions in other parts of the basin and in other ocean basins around the world. Oceanic lithosphere lies at the bottom of the ocean. But what's interesting to me is the age progression. So underneath this location right now is where we find the oldest crust in the Pacific plate. And then as we travel to the east, as we get further and further away from this spot, the oceanic lithosphere gets younger and younger. And eventually you might run into a spreading center, such as the Juan de Fuca Ridge, which separates the rather petite Juan de Fuca plate from the larger Pacific plate. And that's a place where new Pacific plate is being made. Again, that process of seafloor spreading that decompresses the underlying mantle, generates mafic magma, that wells up and seals shut the crack between the two plates, maybe erupts onto the seafloor, makes some pillows. And then the whole thing, from that point on, cools off and moves away from the constructive plate boundary. And as it cools off, it gets denser and it subsides, and it travels laterally tremendous distances, thousands of kilometers. The oceanic crust that is old is oceanic crust that is cold. And cold oceanic crust is dense. The lithosphere, the mantle part of the lithosphere is built out on the bottom part of the plate and has basically made it heavier than the surrounding material. And that helps drive this subduction, this slab pull that helps yank on the overall plate and helps basically drive plate tectonic processes. By understanding the origin, evolution, and ultimately the destruction of oceanic lithosphere, we arrive at a better, safer understanding of the planet that we inhabit.